Thank you. So today I want to talk to you about how to model blockchain protocols and then how to reason about or analyze the security of blockchain protocols. And so there's a few things to think about when we're trying to model these protocols. The first one is, what do we mean by a blockchain protocol being secure? So that is, what kind of properties do we want these protocols to satisfy? And these are things that Sarah brought up, like consistency, liveness, chain quality. And can we use the same definitions for a broad range of protocols? So when we're talking about things like we heard earlier today, well, not necessarily a chain, but you have a tree-based blockchain protocol or some other DAG-based blockchain protocols. Can these definitions be flexible enough to analyze different shaped blockchain protocols? And then what about the network? So these protocols, right, they run on top of the internet, which is a complicated thing to model on itself, but really we're talking about a peer-to-peer network on top of the network. So how do we reason about things like network delays? When we have some general understanding about, say, the distribution of network delays, this is very old data, but still mostly accurate. So how do we incorporate these distributions into our model? And then thirdly, what about the attacker? How do we model attacks on our protocols, and how do we consider both attacks that we know about and also attacks that we haven't even thought of? So how do we model any kind of attacker? So in this talk, I'll be going over a simplified model for blockchain protocols, and one that allows us to both give really concrete bounds on security and also capture what any possible adversary could do. I'll define what I mean by security, and for this talk, I will be using consistency here to be security. So again, if the property that says that we all agree on what the blockchain is, we all have a consistent view of what the blockchain is. And then I'll use Nakamoto's protocol as an example of how to use this model, and also show an attack on Nakamoto's protocol and how it falls into this model. So when we talk about blockchain protocols, there's really two parts. One is this pi, which is really the mining rule. It's what we're interested in. It's our base protocol, I guess our layer 1 protocol. And then C is kind of everything else that you can build on the blockchain. So if you have some sort of DAG-based protocol, and then C might be how you extract a linear sequence of transactions from that DAG. But for this talk, I'll be focusing on the pi protocol. And so when we talk about the model, I'm going to be talking about a typical execution of the protocol. So if you were to run the protocol, what is the expected behavior you're going to get? And in this protocol, we have what we call an environment, which basically models who starts off as honest and corrupt, and also some messages that I'll be talking about. So here in our model, all players are miners, and then you have some that start off as honest, running the pi protocol, and some as corrupt, controlled by the adversary. And I'm also going to model the network as the adversary having full control. So if an honest player wants to tell other players about a block they've mined, they are going to tell the router, so the adversary, and then the adversary is going to be in charge of delivering these blocks to all other players. And the adversary is limited by, I guess the adversary can then control the order of how messages are delivered, but the adversary will be limited by some maximum delay that they can impose on a block. And so this is how you get the asynchronous model or the bounded delay, I guess a partial synchronous model or the bounded delay model. And so in the model, we have that our smallest unit of time is going to be a round, and in a round, a few things are going to happen. You have that the environment is going to send out the messages to all the players. These are transactions or whatever the players are going to include in the block. And then the adversary is going to look at everybody's state and decide who's going to be corrupt and who's going to be honest. So the adversary can choose who to corrupt and might have to choose who to uncorrupt so that there is a maximum fraction of corrupt players at any given point. And once the adversary has made this choice, now everybody tries to mine. And we model mining using a random oracle. So every player in each round gets one chance of mining, one call to this oracle, this h of x, asking, hey, can I mine at this round? And then They can make as many calls as they want to this verify function. So if they've heard about blocks, they can ask the oracle if these blocks are valid without having to give up their chance to mine. And then if the adversary controls queue players, the adversary is going to get to make queue queries to this oracle. And we give the adversaries a little bit more power here and say that they can make those queries sequentially. So if in one of those queries the adversary finds a block, they can then move on to working on the next block. They don't have to waste the rest of the queries on the same block while the honest people are all mining in parallel. So the whole point of using a random oracle to model mining is so that basically mining is like flipping a coin. Your best, the best strategy you have for mining is just to try every round. If you fail, try again. There is no ASIC in this model. And again, you can always verify blocks you've heard of without having to infringe upon your ability to mine. So to summarize what the adversary can do here, they have dynamic control of who to corrupt and who to uncorrupt. They have full view of all the states. They can make these queue sequential queries to the random oracle every round, and then they can reorder all honest messages, and they can delay honest messages, but they must deliver honest messages by some maximum amount. But they can always withhold their own blocks. There are no rules about what they can do with their own blocks. And so the parameters in this network are delta, which is going to represent our network delay. So the adversary can delay blocks up to delta rounds. We have the probability of mining, and this is in terms of this variable c, which roughly means that a block is going to be found every c times delta rounds. And then you have rho is going to be your maximum number of fractions, and then mu, your maximum number of adversary, or I guess your maximum fraction of adversarial parties, and mu is going to be your honest fraction. Right, so there are, like Sarah mentioned before, several different properties that blockchain protocols could satisfy. We're interested in consistency. And consistency roughly means that if you take 2 points in time, R and R prime, and 2 players, one who's honest at time R and one who's honest at time R prime, look at their chains, cut off some constant number of blocks at the end, their chains should agree completely. This also means that if you look at what you believe to be your chain now and then your chain in the future, you always agree with your future self. So it's sort of this common prefix, but with respect to time as well. So when we look at bounding consistency, we look at the relationship between the C, the probability of mining, and then the maximum fraction of adversary you can withstand, or the protocol can withstand. And so we see here this blue line, this lower bound of consistency for Nakamoto's protocol. So for whatever fraction of, whatever probability of mining you have, what's the most power the adversary can have before consistency is no longer guaranteed. So if we take Bitcoin's network delay to be 10 seconds, which is probably more than is accurate, then Bitcoin would be at about C equal to 60, so blocks every 10 minutes. And you see here that basically consistency for Nakamoto's protocol is as good as it gets. The red line here represents a delay attack similar to the 51% attack, and that's not going to happen when C is equal to 60 in this model. And then if you take Ethereum, say like 12, 14 seconds, then you see consistency is really only guaranteed in this model up to about a third of an attacker. And so here you see the relationship between sort of mining hardness and how much you can withstand an attack. And so if you have blocks coming out faster, you're going to get your C to be smaller, and you're going to have a less resilient protocol. Or if you have, say, bigger blocks, or your network delay is bigger, you're also going to get that your C is smaller. And again, you're less resilient to attacks on consistency. Or you have less guarantees, I should say. So how exactly do we calculate these bounds? So how do we analyze consistency? Well, to begin with, why do blockchain protocols even work? How is it that we ever manage to agree on a chain? So if you take a moment of time where nobody mines, say the last block in our chain is block A, we're all trying to mine to increase the chain after block A, and say at some point Bob goes and finds a block. Now Bob's going to tell everybody in the network about his block, say this time is at least the network delay, At the end of this, we've all heard about Bob's block. We all agree that Bob's block is the one true longest chain in the network. But say that while Bob's block is being broadcast, Alice goes out and finds a block. Before she hears about Bob's block, she tells some people in the network about her block, and then now we have a fork in the network. We have this disagreement. And what keeps this from happening ad nauseum? What keeps this from happening nonstop? Well, there has to be some correlation between the network delay and how long it takes until the next block is found. So this is where we rely on an event called convergence opportunity. So convergence opportunity is a 3-step event, which we call this delta hit delta. So the first step is that you have delta rounds where nobody minds. So at the end of these delta rounds, we are guaranteed that we have all heard about all the blocks in the network. And then if you have one player that mines a block, then this is the single longest block. We haven't heard about it yet, but in terms of the global view of the network, this is the one longest block. And then say another delta rounds pass when no one else mines. Then by the end of these delta rounds, we have heard about the block from step 2, and we all agree, okay, this is the longest block, and we all have heard about it. The caveat being that we can only talk about what the honest players are doing. We don't know if the adversary is hiding anything. But these are opportunities where every honest player is going to agree on a block, as long as the adversary doesn't interfere. So in our analysis, we want to say that the adversary can only break consistency if they're able to interfere with every single convergence opportunity. So looking at a period of time, look at how many convergence opportunities do we expect, and then what can the adversary do with those. So how do we count these convergence opportunities? Well, we look at a period of time, say of T rounds. We look at all of the blocks that the honest people have found. We call these the honest hits. And the time between those blocks. In this case, these blocks are all found with more than delta rounds between them, so these are all convergence opportunities. Now, if an adversary wanted to break any of these convergence opportunities, what the adversary would do would be to insert one of its own blocks in the middle of the delta silence, making it no longer a delta silence, and so introducing sort of these little forks into the chain. And so what we want to do is count exactly the number of convergence opportunities that we get in T rounds, and then say that the adversary needs at least those many blocks mined in those rounds to be able to break consistency. At the bare minimum, it needs to interfere with every single one of those convergence opportunities. Otherwise, the honest people have at least one chance of converging. And when we're doing this count, we have to keep in mind that blocks may be found at separate intervals, and so we need a very specific way of doing this count. And that's where, So now I'm going into how exactly we do this count for Nakamoto's protocol. So this specific counting is really great to do with MARKOV models. And MARKOV models, for those of you who aren't familiar, are models where you basically have different states that you could be in, and then how to transition between those states and with what probability. So for our MARKOV model for Nakamoto's protocol, it's super simple. It's only 2 states that you could be in. State S0 is what we call the messy state. This is the state where you have no guarantee of consistency. Blocks are being found really close together. Again, the honest blocks are really being found really close together. Everything I talk about is in relation to what the honest people are doing. And so to exit state S0, that's when you have those delta rounds of silence, those delta rounds where nobody minds. And so this is a chance where you might get a convergence opportunity. So once you're in state S1, if the next thing you get is somebody mines, and then again delta rounds where nobody mines, then you're converging. You stay in state S1. Otherwise, if 2 blocks are found really close together by the honest people, you go back to that messy state. So when we want to count the convergence opportunities, that's what we're going to count, this edge from state S1 back to S1. And basically, that's how we get our count. We look at a random walk on this MARKOV model and say that for T rounds, how many convergence opportunities do we expect? And we get our bound here, which says that as long as the fraction of events that are convergence opportunity is greater than the fraction of events that are adversarially mined blocks, then we are solid. We have guaranteed consistency. In sort of easier to understand words, if you look at T rounds, as long as the number of blocks the adversary needs to break consistency is more than the number of blocks the adversary could possibly mine in expectation, then we have guaranteed consistency. All right, and so now I want to go over a simple attack on consistency, or consensus, I guess both. This is similar to the 51% attack, except for we're adding in this notion of the adversary having controlled the network. So in this attack, what the adversary does is they delay all honest blocks the maximum amount by delta, while they secretly mine their own longer chain. So the whole goal of this attack is for the adversary to thwart the growth of the honest chain while secretly mining a faster, sort of more efficient chain, since they don't have a delay between their own blocks. And as I said before, so this is the red line that we get here. And so for Bitcoin, you see here that this attack basically doesn't work, because at 50%, like that's basically any attack would work at that point. But what the red line says is the probability of this attack succeeding indefinitely. But if you're making a transaction, you don't really care if an attack is going to succeed indefinitely. You care if it's going to succeed for 6 blocks, or 10 blocks, 15 blocks, however many blocks you're going to wait before you accept the transaction. And so what we do is we figure out a way to calculate the probability the attack lasts for any given number of blocks. So we did this with a slightly more complicated Markov model that I won't go into too much detail. You can check out the paper if you want to get more. But essentially what this is doing here, it's keeping track of, say, the adversary's chain and then the honest chain, and saying like by how much longer is the adversary's chain than the longest chain. So say S0, both chains are of equal length. And then say S1, S2, S3, that means the adversary's chain is up by 1, 2, or 3 blocks. And while say S1, it means the honest chain is growing faster. And here when I say honest chain, I mean like any longest possible honest chain. And so from this, we can calculate the probability that the attack lasts for some given number of forks. So for looking at 3 different values of C here, and say C is equal to 60 is about Bitcoin. And for a 49% adversary, you see that it's actually pretty likely that the attack lasts for a pretty significant number of forks, of blocks. But 49% adversary is pretty strong, right? So we can look at different percentages, say a 33% adversary or a 25% adversary. So for an example here, if you were to wait 9 blocks before you consider a transaction confirmed in Bitcoin, and there was an adversary with a 25% of the mining power, in this model, there would be about 1% probability of your transaction being reversed. So this gives us a way of being able to understand your risk when it comes to transactions, and maybe in a stronger model than might be 100% realistic, but if you're talking about the probability of, say, a large transaction going forward, maybe you want a little bit of a stronger model when you're calculating your risk. And so the other thing we did in the paper, which I'll go over briefly, is look at different kinds of blockchain protocols, not just the single chain. So we have what we call the click chain, where instead of having one chain, you have multiple chains that all reference each other. So if you're mining a block, say block 1 on chain A, you're going to have to not only point to block A0, but also to block B0 and C0. So basically you have this like clique of pointers that you make at every level. And interestingly, we found that no matter how many chains you add, your consistency lower bound is still the same. So if you, say, have 10 chains instead of 1 chain, now your blocks have to come out at 1/10 the speed, or I guess your chain is going to grow at 1/10 the speed, so your blocks are still, each individual block will still have to come out at the same rate for you to have the same consistency guarantee. So you can't just like add 20 chains and expect that you're going to be able to keep the same consistency. But if you look at that same attack, and here analyzing that attack for 1 chain, 2 chain, and 3 chain, we see that the more chains you add, the more resilient the protocol becomes against that attack. So basically, once you have 3 chains, you're still going to have the same like block rates over like all the chains, but that attack basically doesn't work anymore. That's not to say that there isn't a better attack for it, but at least in this model, at least for this attack, it becomes more resilient. And we also took a look at Ghost, which you've heard about today a bit. And again, we find that Ghost has the same consistency lower bound as Nakamoto's protocol. So for the same block rate, you get the same guarantees on consistency. Not to say that there might be a better lower bound for Ghost that we haven't found. And so So the delay attack doesn't work on ghosts anymore because of the way that you're choosing now how to mine. And so we'd look instead at a balancing attack for ghosts, which I think we heard something similar earlier, where the adversary is trying to keep the honest people power split between two possible chains. And it's a little bit more difficult to analyze. And so this is sort of a snapshot of what our Markov model looks for that. It's really like 3 layers of infinite chains. But what we're able to do with it is do a similar kind of analysis for the probability that the attack lasts for any given number of blocks. So sort of like what your confirmation time should be if you assume this attack is going on. So sort of to summarize that, what we do is we simplify the model quite a bit so that we can get these really concrete bounds on security, and then we are also able to apply this to different models of blockchain protocols, different like versions of like DAGs for these protocols, and be able to reason about different attacks. And if you want more information, I'd say check out my paper. And yeah, I'm happy to take questions now.
Great, thank you, Lucianna. Are there any immediate questions from the audience? Well, I have a question. So if I've understood your presentation correctly, your model helps you understand the probability of certain attacks under certain conditions on a blockchain. Is that more or less right?
It allows us to also, be able to model attacks, yeah.
Okay, and then is the link to scaling that you would be able to change those conditions and understand what the security implications of a different protocol would be? Yeah,
exactly. Or if you be able to also use the model to analyze maybe like a new DAG protocol that you come up with and see like how it compares to other protocols using the same assertions, like using the same model to analyze more the different kinds of protocols. Yeah.
Cool. Okay, well that sounds really useful. We have a question here.
Thank you. I'll definitely check your paper. It looks really cool. So you've talked a lot about consistency. Like, do you in your paper, or do you plan to use like similar model to analyze, other like security property, like chain quality or liveness? And do you think that you could use like the same Markov thing to analyze that, or did you do it already?
Yeah. So liveness, I guess, like chain growth is incorporated into consistencies. So part of the analysis there is we have to have some lower bound on how fast the chain is growing. So that's part of the model that I didn't mention. And then chain quality, you can do very similar analysis, but sort of like the selfish mining does the Markov model analysis for chain quality. And we did look a little bit at that to find sort of the lower bound on using like a similar attack for, I guess, Ghost is a little bit more difficult to talk about in the same way because you do have like chain, like tree quality maybe is what you're going for, unless like you're still extracting one chain. But yeah, going on to other protocols is definitely our future goal.
I just wanted to ask, when you were doing the analysis and you had the little graph of the adversary's power and the number of blocks, is that just basically saying that the adversary can mine 9 blocks on average with some likelihood faster than the rest of the network?
Yeah, that's like if the adversary were to start the attack right now, what's the probability that they're going to be able to mine 9 blocks faster than the honest chain's going to grow by 9 blocks?
Yeah, I was wondering, could you extend that in the sense that could you pursue the selfish mining strategy where if I'm 2 blocks ahead, then maybe I release a block, so then you sort of reveal your block over time as opposed to all at once? And would that have any difference?
So it's a different kind of attack. So that one is an attack on chain quality, right? Yeah. This is an attack on consistency. So this is making sure that we are not reaching consensus on what the chain is at this point. Yeah.
There was a question there at the back, and then we'll go here.
Yeah, if I understood correctly, your delta is the upper bound for a delay to reach all honest miners, basically, all honest nodes. So we're only talking of miners. Okay, but that's 100%. So, but normally the propagation is more or less a long tail distribution. How would that change if we make that, I don't know, 90% coverage or 85% coverage? Could that be incorporated into your model?
Yeah, so right now it is definitely a conservative estimate. But again, to get like really concrete lower bound and security, you do want to say like the worst case. But we are looking in how to maybe incorporate like the probability that the block reaches different nodes in a network with some distribution instead of just like one maximum amount. I think that would give us a little bit more of like leeway of work, because at least you can compare like some sort of optimal case to some like more realistic case. Yeah.
Thanks for the great talk.
Thanks.
There's one more question back there.
Thank you for the talk. So I have a question about, does this model also extend to permissioned kind of blockchains? Or does it really require there to be proof of work kind of functionality?
So it requires there to be some sort of proof of resource. So the main idea behind using a Markov model is that you have to have the probability of events being independent of each other, which becomes a little bit trickier when you talk about permission settings or proof of stake settings. Yeah.
Okay, thank you.
Were there any other questions at this stage? Chris?
So when you talked about the DAG model, you did say something like you weren't worried about delays in this, where you might mine and like the adversary might keep hold of a block or not reveal it, right? You were interested in only splitting. Was that right, or did I understand that wrongly?
No, we do take into account the adversary withholding its own blocks.
Okay, even in the DAG model.
Yes.
Okay.
Yeah.
Yeah. Okay. Great.
It's just a bound on what the adversary can do with honest blocks. With its own blocks, there are no rules.
Great. Well, then we will move on to our next presentation.